Alright, so today we're going to continue with Chapter 8 and rotational motion. We're going to cover just a little section on kinematics for rotational motion. So you should recognize these equations that are on the screen here because they're almost exactly or very, very close to our kinematics equations we used for translational motion, which is motion that's not in rotation. Okay, so what I would like for you to do is go ahead and pause the video now and get these equations written down. You don't need to copy down this column again. You already have all of these equations. These are the kinematics equations we use for all of the first semester for regular objects in motion. These rotational motion now kinematics equations, you should notice have some of our new variables in them. Be careful to note that this is omega, which is angular velocity. This is alpha, which is angular acceleration. And this delta theta is our angular displacement, so how far or what chunk of the circle has been covered during that point in time, and that angular displacement or theta is measured in radians. Alright, so it's important for us to understand that these kinematics equations are again for uniformly rotating objects. These are for things that are moving at constant angular acceleration. As it's spinning, we have a constant acceleration, so we're moving with, again, a constant or an unchanging acceleration. It's speeding up or slowing down at a constant rate. So let's go ahead and just try some practice problems here. Go ahead and pause the video now to get the problem written down. First thing we need to look at here is that 9.8 centimeters needs to be converted. So our radius then becomes 0.098 meters, right? Because we move that decimal place 2 to the left. All right, we've got a rotational speed of 14 radians per second. Rotational speed sounds different to us, but we need to make sure that this radians per second is a very good indicator or a very good clue that means it's angular velocity or omega. Okay, so even if you're having trouble picking it up with the terms or with the lingo, you can pick it up with just the units itself. Okay, if the ball's rotation slows at a constant rate of 2.4 radians per second squared, how far will it roll before coming to a stop? That means alpha is this. Okay. If our angular velocity was initially positive and we are slowing down, that means our acceleration needs to be negative 2.4 radians per second squared. Okay. We want to know how far it will roll before coming to a stop, which means essentially we're solving for distance, okay, or L. Okay, and I'm going to write my L as a cursive L so make sure you understand it's not a 1. In order to get there, however, we're going to have to solve for delta theta, right? We need to find out how many revolutions it made during that time, or what chunk of the circle has it rotated during that time. If it's rotated more than one full circle, that's going to give us a much longer length, and we're going to be able to find out how many rotations it's covered during that time. It's also important for us to see that since it's coming to a stop, our final angular velocity should be 0, which means our 14 is really our initial. We need to go ahead and put that subscript in. Alright, so now that we've got all of our variables in consideration, we need to look at those angular kinematics equations to determine which one we can use to help us solve for theta. Okay, remember our overall goal here is going to be to find the distance it comes or it rolls before coming to a stop. But in order to solve for distance, or that L variable, we need to have theta and the radius. We have radius, but we don't have theta, so we need to solve for that angular displacement, or what chunk of the circle has it covered, how many radians has it covered during this time of rotation. Okay, so looking at our kinematics equations, we should use the last one, right? Omega squared equals omega initial squared plus 2 alpha delta theta. Okay, we use this equation because we weren't given a time. It doesn't tell us how long it takes to come to a stop. Okay, so we know our final angular velocity is 0. We know our initial angular velocity is 14. We know our angular acceleration is negative 2.4, and we're solving for theta. Okay, so we're going to go ahead and move this to the other side. And we get theta equal to 40.8 radians. Okay, remember that theta tells us what chunk of the circle has it covered during that rotational period. So here it's telling us that we've covered 40.8 radians worth of the circle. So we know that happens to be more than one rotation, but that's just what we're measuring in right now as radians. Okay, from there, we can take our angular displacement and plug it into this top equation right here to solve for the distance traveled. So since we want to find out how far it's gone, we're going to solve for L. We know that theta is equal to 40.8, and we know that the radius of this particular circle is 0.098 meters. Okay, that gives us a distance traveled of 4 meters. All right, our next one here, go ahead and pause it to get it written down, and then we'll go ahead and start working. All right, first thing, this tells us that it starts from rest, so that we know our initial angular velocity is 0. It accelerates to a final angular velocity of 25,100 RPMs, 25,100 RPMs. Okay, that is not the correct unit. RPMs is a version of angular velocity, but it's not the correct version. We need it to be in radians per second. So we're going to have to do a conversion there, and we can use our shortcut, taking it times 0.105. Okay, so 25,100 times 0.105 is 2,635.5 radians per second. Okay, remember you can do a T-chart for this, no problem. 25,100 revolutions per minute. 1 minute equals 60 seconds. 1 revolution equals 2 pi radians. Okay, that's all I did. I just took that shortcut that we solved for right there. You're going to get about the same answer. Okay, the next thing they tell us is time. We know that time is equal to 3.2 seconds. What's the angular acceleration? We're going to answer just the first question first. So angular acceleration, we can use our very simple kinematics equation here. So omega final equals omega initial plus alpha times time. And we know final angular velocity is 2,635.5 equals 0 plus alpha times 3.2. Okay, which gives us an alpha, or an angular acceleration, equal to about 823.6. Units for that are, of course, radians per second squared. So now we're going to go ahead and solve for angle through which the drill has rotated. So that means we're going to solve for theta. We want to find out what chunk of the circle that drill has covered during that time, or how many radians worth it's rotated, which means we're going to solve now for theta, or delta theta. Okay, we've got our angular acceleration, we've got our time, we've got any variable we want, so we can really pick any equation we want to solve for that. We'll go ahead and just use the equation that solves specifically for delta theta, which is initial velocity times time plus 1/2 alpha t squared. Our initial angular velocity was 0. Our alpha we solved to be 823.6 times t squared And after doing the math there, it gives us a theta value equal to 4,216.8 equals delta theta. Okay, and our unit for theta is always radians. It doesn't ask us for the number of revolutions or the distance traveled, so since it asked us for the angle, that means we were solving for theta, and our angle is in radians, so we can stop our answer right there. All right, our last practice problem here. Go ahead and pause the video to get this written down. If you want to try and start this one on your own, you can. This does have two specific parts to it, so we're going to work through it together if you want to follow along. If you'd rather just practice it on your own and then see if you match at the end, that's fine too, and you can watch back if you have it incorrect. Okay, so this tells us the washing machine starts from rest and accelerates to an angular velocity of 5 revolutions per second in 8 seconds. Alright, so like I said, this one has two parts to it. The first thing that we're going to do is look at this first section of the problem. A washing machine starts from rest, so we've got an initial angular velocity of 0, and accelerates to an angular velocity of 5 revolutions per second. That's really important that we understand it's not radians per second. This is revolutions per second. We need to convert that 5 revolutions per second to radians per second. Okay, and the way we do that is to convert revolutions to radians. So we know that 1 revolution is 2 pi radians. Okay, so we're going to take 5 times 2 times pi, divide by 1 equals 31.42 radians per second. Okay, so instead of using the 5 revolutions per second, we're going to use 31.42 radians per second. Okay, that's really important. The time for this section of our problem is 8 seconds. Okay, we want to find out for this portion how many total revolutions does the machine go. So for this first portion of the problem, we need to find out how many revolutions or how many complete spins did this washing machine take to reach this speed. Okay, so in order to do that, we want to find the total number of revolutions. In order to do that, we need to solve for theta. We need to find out what chunk of the circle has it rotated through. Okay, how many radians has it spun through as it's beginning this motion? Okay, so we need to solve for delta theta. Okay, in order to do that, we've got to solve for alpha as well because we don't know our angular acceleration for this portion of the problem. Okay, so we've got a couple different things we have to do here. So first thing that we're going to do is solve for alpha, solve for our angular acceleration, because we can't solve for theta without an acceleration. Okay, so we can use our initial, or our first simple equation here, omega equals omega initial plus alpha t. Here we have 31.42, that's our final angular velocity. So we're going to take 31.42 divided by 8, and we get alpha equal to 3.92 radians per second squared. Okay, that gives us our angular acceleration for the first portion of this washing machine experience, I guess. Now we need to go ahead and solve for delta theta. Okay, so I'm going to go ahead and use this equation. All right, for the first portion of our example, we don't have any initial angular velocity, so theta is going to be equal to 1/2 3.92 times 8 squared, which gives us a theta value of 125.7 radians. Okay, so this tells us what chunk of the circle it's covered during this time, how many radians has it spun through. It doesn't tell us the total number of revolutions, but we need to convert to find the number of revolutions. Okay, so how do we convert from radians to revolutions? What's our conversion factor? Okay, we know that 2 pi radians is equal to 1 revolution, right? 2 pi goes on the bottom, because we're trying to get rid of radians and we're trying to end up in revolutions, which means we're going to take that 125.7 divided by 2 divided by pi, or 125.7 divided by parentheses 2 times pi. Okay, be careful about plugging that into your calculator incorrectly. We should get a value of 20 revolutions. So what this tells us is that during that initial time when the washing machine started from 0 and sped up to 31.42 radians per second, it spun exactly 20 times. And technically a little over 20, but pretty close. Okay, it spun 20 times. That's only the number of revolutions for the first portion of our problem here. Okay, so now I'm going to switch colors so we understand this is the second part, but we're going to look at the second portion of our example here. It says, after this, the machine comes to a stop in 12 seconds. Okay, it comes to a stop in 12 seconds. So I'm going to get rid of all of this work here, so if you're not quite done, make sure you hit pause so you can get it all written down. And we're going to go ahead and look at the second portion of our example here. The machine is unplugged and comes to a stop. So we know that final angular velocity is 0. Our initial angular velocity is still going to be 31.42. Okay, because it's reached a speed of 31.42 radians per second, and then it comes unplugged. So this second portion of the example we're looking at here is from the second it becomes unplugged to the time it comes to a stop. Okay, so initially here it's traveling 31.42 radians per second, and it's going to slow down to come to a stop. Okay, and it tells us the time it takes to do that is equal to 12 seconds. Again, we want to solve for delta theta, but in order to do that, we have to solve for the angular acceleration during that time. So we can use our easy equation to solve for angular acceleration. 0 equals 31.42 plus alpha times 12. So negative 31.42 equals alpha times 12, which means alpha is equal to negative 2.61 radians per second squared. From there, go ahead and solve for theta. This time we have an initial angular velocity of 31.42, so we can't leave that out of our equation. Make sure that you include the negative for your acceleration. And I end up with a theta value somewhere around 189.12 radians. Final step there is going to be, again, to convert radians. So 2 pi radians is equal to 1 revolution. So we're going to take 189.12 divided by 2 divided by pi and get 30 revolutions. Okay, so total, our machine travels 20 for the first portion, 30 for the second portion, which gives us a total value of 50 revolutions of this washing machine during this particular example.